Thank you, Anthony, for the nice introduction, and thanks for having us today. A warm welcome also from my side. My name is Sanna Leinius, and I'm Product Market Manager at Basler. I work closely together with Martin, who is also Product Manager, and Martin is with me today.
Hey, good morning.
Both of us are responsible for Basler's 3D image acquisition products. Today, in the following 30 minutes, we will show you the benefits of the time-of-flight technology in logistics. And this will include a short live demo. Afterwards, we'll have about 15 minutes for your questions. And in our presentation, we will refer to Basler's 3D camera, the Basler Blaze 101. So if you are working with a different time-of-flight camera, certain features may apply or may not apply. So let's start. And I'm going to switch off my camera to free some bandwidth. So let us first have a look on why machine vision is becoming so important for logistics. The growth in e-commerce is phenomenal during these times. At the same time, we see increased requirements for flexibility and speed in order processing and delivery. This is strongly driving automation in warehouses, logistics centers, and transshipment points. This graphic from your consultancy uses the example of a tennis ball to show what a complete logistics chain could look like in the future. It is completely automated. After having been manufactured, the tennis ball is picked, unpacked, and transported via robots and AMRs to the port terminal, where maybe in the future, even autonomous ships transport it to its destination. And here again, every step of the logistic chain is automated, up to last mile delivery via drones or robots. And maybe in the faraway future, our goods even determine their best packaging and finding their best route and transport vehicle on their own, based on intelligent systems. The whole automation process already today needs intelligent systems for fast and safe orientation and navigation. And this is exactly where machine vision comes into play. So machine vision includes 2D or 3D vision solutions. And today we're going to concentrate on 3D vision. So here we see 4 application examples with 3D vision. The first one shows obstacle detection and human-like navigation in the intralogistics. So we can see an autonomous mobile robot transports parts to an assembly line maybe, or a packaging place in a dynamic environment. And the 3D sensor is used for navigation and also to avoid collisions. The next example shows presence detection, checking and counting of objects. So a 3D sensor in such a use case could check, for instance, is there enough space left in the container? Are all parts there? Are they in the right place? Does nothing fall out? Such kind of tasks a 3D vision system could fulfill. The third example shows volume measurement and position detection. So the dimensions of a freight object significantly determine the transport costs, of course. So with a 3D sensor, the volume of even irregular shapes can be easily determined as they pass by. And last but not least, there are also a lot of robot-controlled gripping tasks in logistics. This could be bin picking or machine tending or other pick-and-place tasks like palletizing, depalletizing, and pick and drop. And it also includes collision avoidance. All those tasks can be done very flexible with 3D vision technology. I would now like to hand over to Martin to go more into detail about time-of-flight technology.
Thank you, Sanna. So when you decide for a 3D sensor, please consider the following points. Number 1 is precision. It must meet your requirements. The camera should also be fast enough. So speed is another aspect. Number 2, the camera must be robust, stable, and compact. it should function for many years in the environment of fixed or mobile robots. Number 3, in warehouse and transport, you have to deal with very changing light conditions. The camera should not be disturbed by daylight in particular. Number 4, 3D cameras with active measurement methods often interfere with each other. Your camera should be able to handle it. And number 5, the camera provides 3D data only. An application software must evaluate this data. For this purpose, the camera must be easy to integrate into different systems. The Blaze 101 addresses all these points, and on the following slides, I will show you why. So for the application mentioned by Sanna, we recommend a reliable and precise 3D sensor. Basler Blaze camera determines distances by measuring the time of flight of a light signal between camera and object. Here we can see a breakdown of the Basler Blaze 101 camera to give you a quick overview of how this device works. The camera consists of 2 boards. The sensor board carries a Sony DevSense IMX556 sensor with a resolution of 640 by 480 pixels and a maximum frame rate of 30 Hz. With this state-of-the-art sensor, we achieve a typical accuracy and precision of a few millimeters. The light signal to be measured is emitted by 4 laser diodes with VCSEL technology, strong enough for up to 10 meters, but still eye-safe with laser class 1. A dedicated lens produces minimal light scattering and provides a wide opening angle of 67 by 51 degrees. On the back of the sensor board, there is an NXP processor. It calculates distances and intensities within less than 100 milliseconds and provides them by a gigabit Ethernet server. This is all neatly packed together within a dust and watertight housing, shock and vibration proofed, with robust M12 connectors. Let's return to the first point in camera selection, precision and speed. These key components guarantee high precision of the Blaze 101. 4 high-performance laser diodes with VCSEL technology, each pulse, exact pulse shape. They also provide high modulation contrast and high peak power. Then there is this optimized optics, high transmission, narrow bandwidth filter around 940 nanometers, and low stray light. And then the perfect image sensor, high modulation frequency up to 100 megahertz, and it also operates in dual frequency timing, 100 megahertz plus 50 megahertz in combination. Oh, pardon. I also want to mention the processor that is inside this camera. The real-time capability is realized by a built-in NXP processor. It does all the depth processing. It has a low latency, so the time between image acquisition and data is ready in the memory of your application is less than 100 milliseconds. It achieves a high frame rate of 30 frames per second, and the whole exposure cycle is about 15 milliseconds in fast mode. So this means you have low host requirements, ready for embedded and real-time applications. For example, we provide a driver for ARM Linux as well, and it can be used for on-the-fly inline measurements. The precision of the blaze point cloud allows you to determine the orientation of the forklift along with its surrounding to automatically guide the lift into the correct position. Precision is the ability to produce the same measurement value over the course of several frames. The blaze has about 2 millimeters of precision typically. However, it is not the same as accuracy. The camera's accuracy, which is the average difference between measured and true distance, is about 5 millimeters within its acceptable range. Above, we are comparing the two outputs. We can see the point cloud clearly defines the open pallet holes for the forklift to interface with the stacked pallets. Whereas other 3D technology needs to make measurements from the scene based on levels of contrast that separates the inside of a pallet hole. If there is not enough light and the contrast is weak, then you may receive poor data from other technology such as stereo. Our approach will give you repeatable measurements that is independent from outside influence and that captures entire scenes in real time. Speaking of real time, some 3D technology utilizes structured light or spinning lasers for scanning a scene. This requires a lot of assembling in the camera, whereas the blaze is capable of freezing the frame, providing you a precise moment in time. The camera works completely without moving parts. There is no wear and tear. Having accurate scene measurement in real time is compulsory for dynamic systems that need to make decisions based on current position data. This could include robotic package handling or pass-fail management systems. To help give a visual representation of real-time scene capture, we have this video. On the left, we have a typical RGB GoPro, and on the right, we have our blaze viewing the same scene. Oops, pardon. As we can see, does not start the video again, sorry for that. As we can see, there are no scanning artifacts and we can track the individual as he moves across the warehouse floor. Another example could be with a robot interfacing a package. In the example above, you see a robot arm that uses the position and orientation of the box defined by the blaze to apply labeling. With a continuous supply of cartons in various orientation, the ability to quickly identify and apply the correct position of the label helps streamline logistical processing time for higher throughput at lower cost and better efficiency. But being robotic compatible is more than just real-time capable. You also need to be robust enough to handle the environment and mechanical movements of machinery. This is why we developed the camera to be an industrial-grade product, so that we function in the same environment as we would expect for robots to work in. To become an industrial-grade camera, you must consider the protection class of your camera housing, where you need machine washdowns or require to operate outside, being an IP67 design, and utilize N12 connectors allow for flexibility in where you can apply your 3D vision system. This in combination with corrosion-proof utilizes a nickel coating that eliminates possibilities for oxidation or being subjected to chemical vapors in corrosive environments. In addition, the movements and impact that could occur with robotic applications are managed by the solid-state design of our camera. This means there are no moving parts within the unit, such as spinning mirror or laser, that are found in other 3D technology. And with its compact size, this allows you to mount your camera in a choice location for your robot assembly to achieve an ideal vantage point. This can be seen in the next example. Due to the camera industrial grade design, one could mount directly to a robot arm to keep the system compact and localized. Unlike other 3D technologies that require independent mount to ensure the quality of their 3D data, this makes the system less flexible and require more time and effort to set up the infrastructure for such system applications, and could require multiple 3D stations to accomplish the same task you could do with a single blaze. To help provide an idea of when your logistics could be in rough or challenging environments, we have this example where we monitor the loading process of an airplane. Since a blaze is an IP67 design with a nickel coating, during rough weather, you could still be able to use the camera outdoors, and chemical used for cleaning the outside of a plane won't erode the camera housing. This, plus the daylight robustness, make the camera an ideal choice for this application. While on the topic of daylight robustness, to help clarify what makes the blaze camera unique is the wavelength that we operate in. The orange line in this graph represents the output of the sun with no atmosphere, whereas the blue line shows how much of that light makes it to sea level. We can see, since the atmosphere has water particles in it, they absorb 940 nanometers light, and that this greatly reduces the effect of ambient light from the sun, but allowing the Basler blaze to function outdoor at sea level. So by taking advantage of the world around us, we leverage our atmosphere's filtering and limit the effect of daylight. So in applications in which the sun is a factor and changing light conditions, the blaze built to handle both indoor and outdoor applications. And you may be telling yourself, well, I work inside a factory warehouse and I don't deal with outdoors. Being ambient light robust eliminates overhead lighting effects affecting your application, along with doors and windows, which brings us to our next example. Even inside factory warehouse, you may need to be able to load from your truck and shipping docks. Typically, these ports are not 100% indoors and can be subjected to daylight. This can be depicted by the sample above, where we can clearly see the beam of sunlight being projected across the cardboard box. But as the output of the blaze shows, this added light does not produce any noticeable effect across the point cloud. Since other 3D technologies such as stereo needs to find common points in the scene to measure distance, one could imagine that an oversaturated image would lead to no data or inability to measure the target. Being subjected to visible light, like our competitors, means at certain level of ambient light, you will not be able to use their 3D approach any further. However, you should be aware of lighting situations that could affect blaze setup. Being able to capture an entire scene, sometimes you need multiple cameras. We have a few tools to help accomplish this, whether it be triggering or precision time protocol, which allows you to synchronize multiple GigE cameras in the same network. The multi-camera channel feature allows you to operate multiple blaze cameras even if they are not in the same network simultaneously, without their light sources interfering with each other. Since you can use our technology with several cameras, this means areas that are normally hidden can now be viewed by another vantage point to capture an entire scene without the need of scanning an object. This can be depicted from the next example. As we can see in this example, if you were to image only one side of the palette, you would be missing half of what was on the other side relative to the camera. But being able to use multiple cameras with different viewing points without one interfering with another You could capture both sides of the palette without having to drive through the docking station both directions. To give you some more real-life examples, we have two applications here. The first on the left is staking and sorting of wood for further processing. Scanning these boards on all sides would help answer, are there enough wooden beams? Are the timbers wide enough and in the correct position? Are there any interfering edges or foreign parts? The second application on the right is loading and unloading hardware for truck distribution. Being able to see all sides of the truck trailer allows a robot-guided crane places and stacks products without the worry of damaging any products underneath of it. And finally, we come to point number 5. This brings us to our last key feature, being the ease of integration into your system environment. For basic setup, prototyping, and benchmarking, we provide our Blaze SDK, viewer, and samples. Using these tools, you could develop your own cost-efficient, effective solution and be able to apply your own image processing techniques to handle 3D extraction. And for those who need image processing but are not familiar with what technique works best for their application, we also support GanyCam standard, and you can leverage image processing software that also use this interface, such as Halcon, Matrox, OpenCV, Point Cloud Library, and so forth. So reach out for your machine vision software providers, OEM, for example, and ask if they support GenTL for ease of communication to our Blaze. And all of those robotic applications, we also have ROS, Robot Operating System, drivers to easily be able to call the 3D data into your robotic system. So yeah, and now we come to something different, our top tip. Now that we have concluded the advantages for the Basler Blaze in logistics, we can cover merging RGB and depth data. We feel that RGBD is a nice feature to make available to developers as certain situations benefit from this extra data. Using the depth data from the Blaze can be merged with the RGB data from a conventional color camera, such as Basler area scan cameras. The output results in a color point cloud, RGB and D depth, in which each 3D point is assigned a color value. This can be helpful for robust object detection and classification, especially with similarly shaped objects. In addition, adding high-resolution 2D images to 3D applications can improve pattern recognition or object detection algorithms. To help describe what is meant by this, we have an example. As we can see here, we have 3 photos representing the same scene. The first 2 are normal Blaze images you would expect from the camera, showing intensity and range data. However, by just using the intensity image, depending on the gap between the 2 boxes sitting next to each other, it may be difficult to define if this is 1 box or 2. Since the edge of the 2 boxes are next to each other and the boxes are the same height, this also does not clearly define the number of units in the system. But by giving developers the added function of including RGBD output by attaching another Basler 2D camera, one would have more contrast to separate the green and the red boxes shown in the last output. Yeah, this is it for the presentation part. And now we switch to a live demo of the Basler Blaze to give you a feeling of how the data could look like and how to tweak the settings of the camera. I start the Blaze viewer. So it tries to find the cameras in the network and opens the first one it finds. But you can select your camera up here. This is the device, the Blaze 101. You see 4 different representations. Unfortunately, me in my home office, in my tiny home office, and the upper left is a point cloud written here. It looks very orange colored. Reason is that the camera by default operates for 0 to 10 meters, but my space here is so tiny that I have only a range of, let's measure that. So the longest distance is probably here. I click on the point. I can do this in any of these images, and then you see it's 2 meters. So let's set the maximum distance for the color coding here to 2.5 meters. So now we have blue and green, and the orange part, the red part is here in the near, from 0 to, let's see what is nearest to the camera. Click here, and you see it's 80 centimeters. So let's start at 70. Then we should see the whole rainbow, and it better differentiates the distances. So as you see, the color for the points in the point cloud are given a false color to represent the distance, in fact, the Z value. And red means near, blue means far away. And here we have a spread from 70 centimeters to 2.5 meters. This is the point cloud. Next to it, you see the range map. The range map is only Z values, so there is no X and Y component. So for this point here on the table, we have in the point cloud, we have for this pixel the X, Y, Z coordinates. And this is a Cartesian coordinate system. The origin for this coordinate system is inside the camera. It's a principal point of this optical system. So it's very close to the center pixel of the center of the sensor. But the range map only gives you that information. And the nice thing with the range map is that it is like a 2D image, although it contains distances, but you can work with it as you used to work with 2D images, run your filters, do segmentation, do measurements in this 2D data as you are used to do. And though the color version here is more for visualization, with your application, you would probably use the monochrome version. It's a mono 16 format, means for each pixel you have a 16-bit integer value, and this directly converts into a distance. You just have to multiply this value by 65,000 divided by 10,000, and then you have the distance. So range map is easier, but you will lack the direction, so to say, the direction information, the X and Y component. And then there is a confidence map. The higher the value, the stronger the signal was returned to the camera. And this is critical for a time-of-flight camera, to have a strong signal, to have a good reflection. So for the keyboard here, for example, which is black plastic, we have a low confidence. And so it gets filtered out from the point cloud you see here, and from the range map. There is no distance data in the default settings. We can improve a little bit, for example, by changing the confidence threshold. Then you will have more points, but most likely they are then less accurate. So confidence threshold, for example, is here. I already added some favorites here to have they directly in access, but you find the whole set of parameters in this tree: image format control, for example, image quality control and such. So a lot of settings to tweak it to your needs. And now let's play with a confidence threshold. When I increase it to the right, it passes through only the data that has a higher confidence than that value here. Confidence for this point, for example, is 22,000, quite strong, I think. Let's go to the right direction. And now it disappears as well. So no data for this space. But where we have a strong reflection here is on my shoulder, for example. So let's go in the opposite direction. And now it passes through all the points. The confidence filter is more or less switched off, but we still have some black spots here. Reason is it's oversaturated, so we need to shorten the exposure time, very similar to 2D cameras, to normal cameras. If it's oversaturated, just shorten the exposure time. We have these parameters here in microseconds, and already at 890 microseconds, it stops oversaturating, and we have filled this gap as well. But let's have a closer look at the point cloud. I maximize this window, and now I use my left mouse button to move around in the point cloud. I shift upwards, so it's quite intuitive to navigate in the point cloud with the control of your mouse. I can also zoom in by using the mouse wheel, and here you see better that is a long list of points that defines a point cloud. They are quite small. I assume over this Zoom transmission, there might be some compression involved. You do not see them so well. That make them bigger. Simply hitting a number 4. So this size, number 3, probably good enough here. And now let's see what happens if we put my iPhone here, or sorry, my smartphone here into the field of view, and we see it's a black surface, no distance data available, and the reason is that the light is from the camera is reflected to somewhere else. So it comes from the camera, but it does not return due to the specular reflection. It goes to somewhere else and it doesn't return to the camera. Let's see if we can improve it a bit by changing to short range mode. So the camera now operates at up to 10 meters. And after 10 meters, it starts at 0 again. This is a typical effect of time of flight measurement, that it repeats every period. And with short range, we use a higher modulation frequency, which gives us even more accurate data. But again, we do not see the surface. If I put my hand here, it now measures indeed the reflection from the light, goes to my hand and then back to the camera. And this results in a longer distance than it should be. So it appears down here. So the message is more or less, be aware that shiny surfaces are difficult to measure, whereas diffuse reflections are easy to measure. I have some walnuts here, put it on my desk, and let's zoom in. You can clearly see them, count them, and maybe even with a robot you can pick them. This is at a distance of 1 meter. You see these 5 walnuts clearly, I think. Okay, well, since time is short, I think I have to stop this here, although there's so many more things to explain. So here we have these black holes. I don't like it. I would like to show you also here we can do something by using the ambiguity filter. So now this hole is also cleared. This is a dual frequency approach we use here, and it combines 2 frequencies and uses this as a filter criteria as well. And with the ambiguity filter, you can deal with those places where you don't have distance data as well. Okay, so this about the viewer comes for free and can be used to understand how the camera works. You also have a documentation window. Click on a feature and then you get a nice description, and you can copy and paste pieces of code to your application. And this brings me to my second example here. I use Visual Studio. Visual Studio, the camera comes with a lot of sample programs, kind of hello world programs. Just open the camera, show a picture, close the camera, or it does some kind of processing and showing some interesting aspects of the camera. And for example, there is one doing this RGBD alignment for a 2D camera and a 3D camera. Let me pick that example. And the first step, you have to do a calibration. And it goes like this. Let me start it. It's a console application, so it opens a console, and then you get, sorry, I have to finish the viewer first. Now the camera is still occupied by the viewer. So let me restart this example here. Connect to top. Okay, and now we see two images. One is the intensity image that comes from the Blaze, a monochrome one, and this is a monochrome version from the color camera. The camera, as we said, as I said, it operates at 940 nanometers, so you might have a different perception with your eyes in regard to reflectivity than you have with the intensity image of the Blaze. For example, the back of my chair is black, also in the visual range, but for the camera, it has a quite high reflectivity, so it appears much brighter. However, for the first step to implement this RGBD feature, you need to do some take some pictures with a checkerboard. So we provide the PDF, you print it out on a DIN A4 paper, for example, and then you hold it in different locations so you clearly see it in both images. Keep your thumb out of these fields, and say save, and a different position, save, press S, save. And when you have a number of images, let's say 10 or 15 of those images, you press C for calculate, and then you have all data needed to do the fusion. So after the calibration, do not change the camera system, please keep it as it is. Do not move the cameras around, and then you can run the fusion example here. Again, it's a console application, so it's all there in source code. Fail to open device, wonderful. Requested is already in use. So what could this be? Let me start it again. Now it works better. So it seems the previous application was not finished completely. Oh no, it's in use. Oh, it's a shame. Oh, sorry. Yeah. Why is it? Let me think about it. Fusion. I start getting nervous because I'm running out of time here. It is still, maybe I didn't finish the previous application probably, and so the color camera is maybe still in use, and therefore I cannot show you the colorful point cloud, which is a pity. But I don't want to spend too much time with troubleshooting now, and I think we should use the final 5 minutes for questions, if there are any questions. So please, I would suggest that you ask your questions now. Actually, I'm not really used to use Zoom. Anthony, maybe you can help.
No, I'm back, Martin. Martin Stanley, thank you very much for that. That was brilliant and very informative. We did have one question that's been answered as we came along about, can we change the basically working range and resolution of the system? And I think Sanya's answered that while we're going along, saying that the sensor illumination lens is fixed and calibrated, so that can't be done. But,
true.
So if anybody else has any questions, please feel free to raise their hand now, and we can allow you to talk and ask a question straight away. So, but I think you answered most questions as you went along. I think there's one item in the chat, so I'll just check that one out. Brilliant. No, that was great. Thank you very much. One thing I would say to everyone who's listening is the proof of the pudding is in the eating. And if someone wants to see a system, if someone wants a demonstration on site, if someone wants to send some samples to us, we can arrange that. We've got demonstration equipment here in Leicester, providing we're allowed to, for COVID regulations, visit you. The sales engineers are more than happy to bring the system to you and do a proper demonstration at your premises. If not, as I say, please do send your samples to us. We can capture some images, do a video, do a webinar, do whatever to show you how well the system works. So thank you very much for listening. Does Sanna and Martin, do you want to say anything else before we finish this one?
Thank you very much for your time and your attention, and please reach out to the OEM people or to us if you have any questions in regard to Blaze. So have a nice day and bye-bye.
Great.
And for me, have a nice day. Thanks for your attention. Bye.
What we'll do now is we'll have a few-minute break and we'll resume at 10 o'clock UK time with Adaptive Vision, talking about how quickly you can set up a machine vision application using their software. So Marek will be ready for that in a few minutes. So I shall see you again soon.